Hello, everyone. First of all, I would like to thank Prototypes for organizing this flash talk. My name is Sharmin, and today I'm going to talk about our work published in Nature Communication at the beginning of this year. This work focuses on understanding the effect of adding liquid metal to boost the stability of zeolite catalyst for methanol to hydrocarbon conversion process. This is a highly collaborative project involving several institutions, including UCCS, Institut Chevreul, Université de Lille, and IPCMS in France, Ghent University in Belgium, Charles University in Czech Republic, Kiel University in the UK, and finally Dongguan University of Technology in China. Right, I will start with explaining the MTH reaction. So this is a methanol to hydrocarbon reaction. We use a feed, methanol feed, which can be either coming from fossil fuel-based source or industrially mostly interesting biomass-based source or directly derived from carbon dioxide. And it is converted to a family of, it can be converted to a family of reaction, which is high-value chemical and fuels composed of either olefins, gasolines, and or aromatics. And typically, we use a solid acid catalyst like zeolites, which are shape selective thanks to their pore structure and network, which determines the hydrocarbon conversion and selectivity. And we can obviously tune the product selectivity by optimizing the catalyst and reaction conditions. So I've got two examples here. One is ZSM5, which is a high silica zeolite having a MFI framework, a three-dimensional pore structure with the medium pore diameter of 5.5. And this, thanks to the size of the pore, this can facilitate a wide range of product and higher carbon chain like gasoline. And SAPO34, which is a silico-aluminophosphate zeolite with a Chabasite framework and small pore diameter, which is suitable for the production of light olefins. So, however, anybody working on catalysis and catalyst knows the problem with the deactivation over long duration in the process. So for this type of catalyst, the deactivation can come from the formation of coke, dealumination, and the collapse of the framework. However, there are some mitigation strategies. For example, we can regenerate the catalyst by calcination at high temperature, and or we can improve the stability by changing the process condition. For example, using a high pressure hydrogen co-feed. Or we can tune the zeolite structure or composition by engineering the porosity or the acid sites. We can also modify with metals such as zinc or gallium. For our case, we want to address the issue of deactivation by adding a liquid metal. So we have used a range of liquid metal, but today I'm going to focus on the addition of gallium. So first, let me talk about the selectivity. But before that, so let me talk about the catalyst. So we have the 4 catalysts, ZSM5 without any addition of gallium. We have gallium oxide supported on ZSM5, which is produced via classic impregnation. We have gallium supported on ZSM5, which is produced via heat treatment. And we have gallium on zeolite, physically mixed. And in terms of the reaction, we have carried out the reaction in a fixed bed reactor, which contains of 2 steps. Step 1 is activation step at 450 degrees under nitrogen for 40 minutes. Step 2 is introducing methanol vapor in nitrogen at 400 degrees Celsius to see the conversion. And here in the figure, it represents the selectivity of the different products. So for example, we have for ZSM5, we have a range of products, including aromatics, which consists of 42% light paraffins, followed by C5 and a small percentage of light olefins. And then if we see the gallium oxide, we see that it favors selectivity towards aromatics about composed of 55%. and a lower selectivity towards C5 products. And then if we look at the gallium mixed with ZSM5, we see higher selectivity towards light olefins and aromatics and lower selectivity towards C5 products compared to that of the ZSM5. We have also carried out a test with hydrogen as co-feeding, and clearly we see changes in the selectivity, which is to be expected. Now, looking at the activity or the stability of the material, here I have a conversion of methanol as a function of time on stream. And as you can see, for ZSM5 and gallium oxide supported on ZSM5 shows a stable conversion of 100% conversion of methanol for 8 to 9 hours, and afterwards losing quite drastically. However, for gallium supported on ZSM5, heat treated and physically mixed displays quite an improvement in the stability of about 30 to 35 hours. And if we see the effect of hydrogen co-feeding on the catalyst stability, we see that for the ZSM5 and the gallium oxide supported on ZSM5 displays a negligible effect. On the other hand, the other two samples, the mixed gallium ZSM5 demonstrates significant improvement of about 70 hours and 110 hours respectively. So for all the cases, we see deactivation eventually. So what's causing the deactivation? And for the gallium samples, we see that there is a clear improvement in the stability. So how is gallium helping with the stability? So in order to answer that question, first, what's causing the deactivation? We sort of know already what's causing it. So that's basically formation of carbonaceous species, which deactivates the active site and can block the micropore entrance. However, we carried out thermal gravimetric analysis to understand and to be sure this is actually leading due to carbonaceous species. Here we have the TG analysis carried out on the spent catalyst after 2 hours of catalysis on ZSM5, gallium or ZSM5 and gallium physically mixed with ZSM5. We see weight loss happening in 2 stages. With a total of 10% for ZSM5. The first one is happening between 100 and 125 degrees Celsius, and the second one between 400 and 550 degrees Celsius. So the first weight loss at 100 could be attributed to the desorption of water, and the second one is burning of condensed graphitic coke. And in all the 3 cases, we see formation of graphitic coke. However, incorporation of gallium displays much lower weightless compared to that of the ZSM5, suggesting that gallium can suppress coke formation and slow down the catalyst deactivation. So next up, we wanted to understand how is the gallium incorporated and how it's helping with the stability. So when we look at the STEM and also the XRD displays no changes in the structure or of the framework of zeolite before or after catalysis. So it's really happening physically. From STEM EDS, we can see some large particles of gallium on the surface. And if we do ultramicrotomic cut, we can see the presence of gallium inside the pores, inside the pores of the zeolite. However, the migration is only happening up to 20 nanometers. So really at the entrance of the pore. Now, if we look at the spent catalyst, the post-mortem analysis of the spent catalyst, we can see that for the ZSM5 without any gallium, the carbon is deposited uniformly on the surface. However, with the incorporation of gallium for both of the cases, we see carbon is localized at the intercrystalline zones. And in some cases, we see large gallium particles covered with surface carbon. So we wanted to understand by using in situ STEM if we can see this migration of the gallium and also the carbon formation. So in order to do that, we have carried out in situ scanning transmission electron microscopy. So that the setup is composed of atmosphere system from prototypes, which is based on MEMS technology. So basically, we have 2 transparent silicon nitride window, and we sandwich the sample in between, and we have silicon carbide support, which can produce heat by a Joule effect, and we can introduce a range of gas. And thanks to the gas setup, we can introduce a range of gas and gas mixture as well. So including benign gas or more complicated gas like carbon monoxide or methane, up to a pressure of 1 atmosphere and a temperature of 1000 degrees Celsius. What's interesting about this particular study is the use of vapor kit has allowed us to introduce vapor of methanol, or we can, in other cases, we can use other alcohol or organic solvent. So in our cases, we have carried out observation on gallium physically mixed with ZSM5. Our interest was to see the diffusion of gallium and formation of coke. So the reaction was two-step. So the first step was nitrogen activation, going from room temperature to 100 degrees Celsius, where we stayed about 2 hours, and then increase the temperature to 450 degrees Celsius for 1 hour under nitrogen. And then we have introduced methanol at its vapor pressure at room temperature, which is about 0.11 atmosphere, composed of 11% methanol, with a carrier gas of 89% nitrogen at 400 degrees Celsius. So this is what the observation gives us. As you can see here, at room temperature, in yellow, we see some particles here as well. The big ones are gallium, and this is zeolite. And with increase in temperature and time, we see loss of some of the areas, and in some cases, we see wetting of the bigger gallium particles. Once we introduce methanol, we don't see much up until 2 hours, and then finally we start to see some migration. And if you look here, after about 4 hours, we see some formation and migration of smaller gallium nanoparticles made up of 2 to 10 nanometers. And this is carrying out surface migration. However, this is as a first study, it was quite interesting to be able to use methanol vapor. However, it was a bit underwhelming in terms of results, partially because we were expecting to see dynamic gallium movement, which did not happen. And the other thing was we had some loss of spatial diffusion information, which can be eventually achieved through ultramicrotomy cut, and we can have information on the diffusion of gallium into the pore of the zeolite. And experimentally, we did not see any carbon formation. Perhaps the duration was too short. So working with age samples might give us that understanding. So clearly, in order to have a profound understanding, one can carry out studies with ultramicrotomy samples, but that would require a lot of trial and error in terms of sample preparation. But clearly, there is an interest in there. So having said that, we still need to understand the role of gallium. Thanks to other techniques, we could eventually have an idea about how the gallium presence can help with the stability of the zeolite catalyst. So we have carried out FTIR. So here I have in situ toluene desorption in drift, and this contribution is related to carbon-carbon stretching in the aromatic ring, which can tell us about the absorption of toluene over time. And if we look at the absorption of toluene, we see that it's lower in the gallium incorporated sample compared to that of ZSM5. And if we look at the residual signal of toluene over time, we can see that the desorption of toluene is faster on the gallium incorporated sample compared to ZSM5. So clearly, this demonstrates that the presence of gallium suppresses the absorption of the aromatic products and enhances their desorption once they are formed on the zeolites. Next up, I have FTIR, which shows the contribution of the hydroxyl group and period absorption vibration. And we can clearly see with the incorporation of gallium, the intensity of OH band decreases. And here I have a contribution in the pyridine absorption. I have contribution of the Bronsted acid site and Lewis acid site. And we can see that the incorporation of gallium decreases the Bronsted acid site, however, have no effect on the Lewis acid site. So clearly gallium changes the acidic site of the zeolite. So with that, I would like to come to the conclusion, as I have shown you, that the addition of liquid metal boosted the stability of zeolite catalyst for the MTH process. We have carried out multiple characterization technique as well as DFT calculation, which I haven't shown, that reveal that the liquid gallium is localized in the intercrystalline area and partially penetrates in the ZSM5 micropores. And the incorporation also modifies the acidic properties, as we saw from the FTIR, slows down the carbon deposition, and in some cases facilitates the desorption of the aromatic molecules. And thanks to the presence of gallium, it provides a continuous refreshing of the acid sites in the intercrystalline voids by removing the coke species and liberating the acid sites, thus increasing the stability of the zeolite. And this effect could be attributed to the high affinity of metallic gallium to the carbon species. So with that, I would like to thank you for your attention, and I would like to thank all the collaborators that have contributed to this study.